My name is Gabriel Avila, and I am a member of Team Miller Indices Lite. The topic we will be discussing today is Miller Indices. Specifically, we will be explaining how the crystal graphic directions work in both cubic and hexagonal unit cells, showing how to convert those directions from cubic to hexagonal and from hexagonal to cubic. Finally, we will show how to translate the origin in order to graphically represent planes in unit cells that intersect coordinate axes.
Hi, my name is Alexia Gutierrez, and today I'm going to demonstrate crystallographic directions. Basically, what we're going to do is we're going to determine the indices for the direction shown right here. This is the tip and this is the tail, and this is my origin, which is where we will be looking at our directions from. To start off with, we have to look at our x direction. As you can see, our x direction is actually starting off at 1 and ending up at 1/2. So our x2 would be 0a, and then our x1 would be negative 1a. So in here, we plug it into the formula. Which gives us negative n. Then we come to our y direction, which is going from positive 1 to negative 1/2. So then we would write it 1/2 b minus 1b all over b, which is going to give us negative 1/2 n. And then lastly, we look at our z direction, which we're going from 0, the origin, to positive 1. So then our our first z2 would be 1c, and z1 would be 0c over c, which would equal positive n. As we know, indices, we do not want to have them in fractions. So what we're going to do is we'll just consider double our n, so n equals 2, and then our direction is going to be -2, -1, +2. Thank you.
Howdy, my name is Charles Kirk, and in this segment of the video, we're going to convert the 0, 1, 1 direction into the 4-index system for hexagonal crystals. So we're going to start with our direction. Then we're going to convert it to our Miller Indices form. So capital U equals 0, capital V equals 1, capital W will equal 1. So in the 4-index system, there's obviously 4 pieces: U, V, T, and W. All these are lowercase. So to find lowercase u, we multiply it by that's u from here and v from here. So, and that will give us 1/3 times 0 minus 1. That will give us negative 1/3. Then we're going to find lowercase v using this equation. So that's v from here and u from here. And evaluating that will give us this will give us 2/3. Okay, to find t, we'll need to take the negative of the sum of u and v, which we've already calculated. So we'll take u from here, that will give us, little u is negative 1/3, and then v is positive 2/3. That will give us negative 1/3. Lowercase w is actually uppercase W as well, so this will just be 1. So then our 4-index system will be this. But this is in the wrong form. We need to multiply it by a factor of 3, so that We only have numbers that aren't fractions. So this will give us
Hi, my name is John Stallings, and I'm going to attempt to demonstrate how to graphically represent Miller-Bravais indices. Now, what you saw in the last segment was a conversion from Miller indices, which are used when dealing with cubic unit systems, to hexagonal coordinates. Now what I'm going to do is graphically represent them. So I'm going to draw in a coordinate system. There's the z-axis. There's the A1 axis, A2, and A3. Now, A1, A2, and A3 are all in the same plane, this bottom plane here of the hexagonal unit system. So what I'm going to do is just look at this, and actually, what's best is to look at the pre-simplified version of the Miller-Bravais coordinates. So I'm going to look at this coordinate here. This is the A1 coordinate, and I'm going to walk -1/3 in the A1 direction. So looks like it would be right about there. Draw a little arrow. Next, I'm going to walk 2/3 in the positive A2 direction. So that's going to put me out here on the edge. Finally, I'm going to walk -1/3 in the A3 direction. And that's going to put us back on the A2 axis, actually right in the corner. The last step is going to be walking up 1 full unit length in the z direction, which will put us right there. Finally, I'm going to draw the direction from the origin, just like that.
Howdy, I'm Ross Dodson, and today I'll be talking about translation of coordinate axes for case of origin interception. Given this unit cell, it is impossible to determine this plane's coordinates, which is why you must add an adjacent unit cell. In this case, this can be used to solve for the coordinate axis of the planes. And for this, you will then get